Hello, and welcome to the Hypnohelix. I'm glad you've joined me tonight. Before we drift away to the red sands of Mars, I'd like to ask you, where in the world are you listening from right now? Whether you're curled up in bed, lying back on the sofa, or sitting in a quiet corner somewhere, I'm happy you're here. If you enjoy these journeys and would like to join me for more, could I kindly ask you to give this video a like? And if you haven't already, please do subscribe. It's the simplest way to travel with me again. And while you're at it, turn on notifications so you'll know exactly when our next adventure begins. It's a small thing for you, but it means the world to me, and it keeps this little community of calm curiosity growing. To those of you already subscribed, thank you. You're the reason these voyages keep setting sail. I'll do my best to make this gentle enough to ease you into rest. Though I must confess, there's always the risk that I make Mars sound just a little too fascinating. If that happens in you, find yourself wide awake. At least you'll be lying there with a head full of cosmic facts to ponder. So, as we begin, let me ask you this. What if the quietest place in the solar system is also one of the most mysterious? Mars, our small, rust neighbor, has been a source of wonder for as long as humans have looked to the night sky. Its steady glow has guided ancient astronomers, inspired myths of gods and warriors, and stirred dreams of life beyond Earth. Yet behind that familiar red shimmer lies a world far stranger and more beautiful than its distant appearance suggests. In the chapters ahead, we will not rush. Instead, we will linger on the frost that creeps across Martian dunes at dawn, on the whisper of wind that stirs the dust, and on the silent scars left by ancient rivers. We will wander through canyons so vast they could swallow entire countries, climb mountains that stretch nearly to the edge of space, and pause to listen to the thin, delicate air sighing over stone. Along the way, we'll uncover the science of how this world came to be, how it once may have been blue with oceans, how it lost the shield that guarded its skies, and how the same forces that shaped it can teach us about our own fragile planet. There will be stories of exploration, too. Machines with wheels and wings, built to endure the cold, to taste the soil, and to send back images of landscapes no human has yet walked. This is not just the story of a planet. It is the story of a companion, a quiet, steady presence in the dark, and of our deep, persistent longing to reach it. So settle in and let us drift together toward the red horizon, where every grain of dust holds the memory of a world that might have been. If you were to step outside on a crisp, clear night and look up, Mars would appear as a small but steady point of rusty light against the darkness. Unlike the cold, white sparkle of most stars, it glows with a subtle warmth, a red-orange ember burning quietly millions of kilometers away. That color is what first set it apart for ancient skywatchers who noticed not only its hue but also its behavior. Most of the lights in the night sky seemed fixed in their positions, wheeling overhead together as the hours passed, but a few, the planets, wandered. Mars was one of these wanderers. Long before telescopes, people noticed that this reddish wanderer did not follow the same steady path each night. For much of the year, it would drift eastward against the backdrop of stars. But then, slowly, it would appear to hesitate, stop, and move backward, westward, before resuming its original course. This strange loop is called retrograde motion, and it was deeply puzzling for early observers. To the naked eye, it seemed almost deliberate, as if Mars had a mind of its own and was pausing mid-journey to reconsider its route. Ancient civilizations gave Mars names and stories that reflected its unusual character. The Babylonians called it Nergal, after their god of war and destruction. The Greeks named it Eris, and the Romans followed suit with Mars, their own war god. The red tint naturally linked the planet to blood and battle, even though in reality its deserts are far too cold and empty for such drama. Yet the connection stuck, and in every culture that tracked its movements, Mars was a figure of significance, a celestial actor with a role to play. The retrograde loops it traced in the sky were one of astronomy's oldest mysteries. In the geocentric model, the belief that Earth sat at the center of the universe, this behavior required some creative explanations. Claudius Ptolemy, a Greek-Egyptian astronomer of the 2nd century, came up with an elaborate system of circles within circles, called epicycles. According to his model, Mars traveled along a small circle, while that circle itself moved along a larger path around Earth. It was elegant in its own way and matched the observations reasonably well, but it was also a mathematical patch on a deeper misunderstanding. The true explanation would come more than a millennium later, when Nicholas Copernicus revived the idea that the Sun, not Earth, was at the center of the planetary system. In a heliocentric model, retrograde motion is not an oddity of Mars itself, but a matter of perspective. As Earth catches up to and overtakes Mars in its orbit, the red planet appears to move backward briefly, much like how a slower car on the highway seems to drift backward as you pass it. Once understood, the motion was no longer mysterious, but it remained just as beautiful to watch, even without modern equipment. Ancient astronomers were remarkably skilled at tracking Mars. The Mayans could predict its position years in advance, and in India, precise records were kept of its loops across the constellations. These observations weren't idle curiosity. They were often linked to calendars, navigation, and even agriculture. A planet's position could be considered an omen, guiding decisions in war or politics. For Mars, with its fiery hue, such omens were rarely gentle ones. Then, in the early 17th century, Galileo Galilei turned his telescope toward Mars. His instrument was modest by modern standards, little more than a tube with a few carefully ground lenses. Yet, it transformed Mars from a wandering light into a small disk. This was proof that Mars was not a star but a world, a place with a surface, size, and shape. Galileo could not see its details clearly, but the revelation that it was tangible was enough to challenge centuries of assumptions. A few decades later, the Dutch astronomer Christian Huygens used a better telescope to make the first known drawing of a surface feature on Mars, a dark triangular region now called Syrtis Major. By watching its position change over time, he estimated the length of a Martian day in just over 24 hours, remarkably close to the modern value. The thought that Mars experienced day and night, much like Earth did, only deepened the sense of connection between our two worlds. Over the centuries that followed, telescopes grew more powerful, and Mars revealed more of its character. Astronomers mapped its polar caps, saw the seasonal changes in their size, and speculated that these were made of water ice, much like Earth's poles. Such findings fed the imagination. If Mars had ice, if it had a day length similar to ours, and if its surface showed shifting patterns, perhaps it also had life. By the late 19th century, some observers, like Percival Lowell, believed they saw straight lines crisscrossing its surface. Canals, he thought, built by intelligent beings to carry water from the poles to the equator. It was an appealing idea, even if it later turned out to be a trick of the eye and the mind. But long before those telescopic illusions, Mars had already captured human imagination simply by the way it moved in the night sky. Its steady brightness and its slow, looping dance made it stand out from all other points of light. It was both familiar and foreign, always there in the heavens, but clearly not like the stars. Around 4 billion years ago, the solar system was not the quiet, ordered place we see today. It was a chaotic disk of gas, dust, and ice, circling a young sun that shone a little less brightly than it does now. Within this swirling cloud, tiny grains collided, stuck together, and gradually grew into clumps called planetesimals. Those clumps merged into larger and larger bodies, each gathering more material through gravity's gentle but relentless pull. Mars was born in this crowded nursery in a region between the Sun and what would eventually become the asteroid belt. The material there was sparser than in Earth's neighborhood, which meant Mars had fewer building blocks to draw from. This scarcity shaped its fate. Mars ended up only about half the diameter of Earth, and with roughly 1/10 of its mass. It was a small planet in a solar system of giants and medium-sized worlds. Size in planetary terms is more than a matter of ego. A larger planet can hold on to its internal heat for longer, keeping its molten core churning and generating a strong magnetic field. That field acts like a shield, protecting the atmosphere from being stripped away by the solar wind. A smaller planet like Mars cools faster, its internal dynamo slowing and eventually shutting down. Without a protective magnetic field, the atmosphere becomes vulnerable, and over time it thins. In Mars's case, this process set the stage for a transformation from a potentially wetter, warmer world to the cold, dry desert we see today. In its youth, Mars was anything but still. Volcanoes erupted across its surface, pouring out lava that reshaped the land. In fact, some of these volcanoes would grow to be the largest in the entire solar system. Olympus Mons, the most famous of them all, rises nearly 3 times higher than Mount Everest and sprawls across an area the size of France. Such immense size was possible because Mars, unlike Earth, has no tectonic plates shifting beneath its crust. On Earth, volcanic hotspots move relative to the surface, creating chains of volcanoes like the Hawaiian Islands. On Mars, the crust stayed fixed over its hotspots, allowing lava to pile up in the same place for millions of years. The early Martian surface also bore the marks of colossal impacts. In the first few 100 million years of the solar system's history, asteroid collisions were frequent and often catastrophic. One of the most dramatic examples is the Borealis Basin in Mars's northern hemisphere, massive lowland thought to have been carved out by a single gigantic impact. If the theory is correct, it was the kind of collision that could reshape an entire hemisphere in one violent instant. Elsewhere, craters overlapped craters, some later softened or buried by lava flows, others left as sharp scars in the rock. These impacts, though destructive, also played a role in shaping the planet's geology and perhaps even its climate. Large collisions can release enough energy to temporarily heat the atmosphere and melt surface ice, leading to periods of flowing water in Mars's early days. Rivers and lakes carved channels and valleys, leaving behind patterns we can still see. From orbit, these watery episodes may have been brief and intermittent, but they hint at a world that was not always the frozen desert it is now. Beneath the surface, Mars's interior was evolving. Early on, the heat from radioactive decay and leftover energy from its formation kept the mantle partially molten. Magma rose, cooled, and solidified into layers, building the planet's crust. Over time, as the heat faded, the mantle stiffened and the crust became thicker and more rigid. Without the slow churn of tectonic activity to recycle rock and release gases, Mars's surface features became remarkably well preserved. On Earth, landscapes are constantly erased and remade. But on Mars, a riverbed from billions of years ago can remain almost unchanged. The lack of tectonics also meant that Mars's volcanoes eventually went dormant. We don't know exactly when the last major eruption took place, but evidence suggests that volcanic activity persisted for much longer than once believed, perhaps as recently as a few million years ago. That's geologically recent, the planetary equivalent of a lingering ember in an otherwise cool fire. In the first billion years of its life, Mars may have had a thicker atmosphere, enough to keep water liquid on the surface for extended periods. If so, it was a climate very different from the one we know today, with clouds, rain, and even snow. Over time, though, as the magnetic field weakened and the atmosphere was steadily stripped away by the solar wind, Mars lost much of its capacity to hold warmth. The planet's once active hydrological cycle slowed, then all but stopped. Water retreated underground or froze at the poles, leaving the familiar dry landscapes we see in modern images. While this cooling and drying marked the end of one chapter in Mars's history, it preserved another. Many of the planet's oldest features remain frozen in time, providing a geological record far more complete than Earth's. Ancient river deltas, lava plains, and impact craters offer scientists a kind of planetary scrapbook, each page telling a story from an era long gone. Today, when we look at Mars through the eyes of orbiters and rovers, we're seeing the end result of these early forces: the violence of impacts, the power of volcanoes, the slow loss of heat and atmosphere. Yet these same forces, billions of years ago, might have created conditions where life could have taken hold, if only briefly. Whether it did or not is still one of the most intriguing questions in planetary science. Mars is small. Size may have sealed its fate as a cold, airless desert, but it also ensured that its surface would remain a remarkably faithful witness to its own past. Every dune, plateau, and crater holds a fragment of that history, waiting for us to read it. The planet may no longer be geologically active on a grand scale, but in the patterns etched into its surface, the echoes of its fiery youth still remain. In the far north of Mars lies a vast low-lying expanse known as the Northern Plains. From orbit, this region looks strikingly different from the heavily cratered highlands to the south. It is smoother, flatter, and stretches for thousands of kilometers, as if some great force once swept across it and left behind an even surface. For decades, planetary scientists have wondered if that force might have been water not trickling, streams or shallow lakes, but an entire ocean. The idea of a Martian ocean is not new. In the 1980s, maps of Mars's elevation compiled from spacecraft data revealed something intriguing. A huge portion of the northern hemisphere sits several kilometers lower than the southern highlands. This difference in height forms a natural basin, one that could in theory have held a body of water covering as much as 1/3 of the planet's surface. On Earth, such a basin would almost certainly be filled with an ocean, and the similarities were too compelling to ignore. Further, evidence came in the form of what looked like ancient shorelines, long winding ridges and terraces that trace curves across the landscape. Some stretch for thousands of kilometers, wrapping around the edge of the northern plains. They resemble the raised beaches or wave-cut cliffs found along coastlines on Earth, where water once lapped and retreated over centuries, while erosion on Mars is slow. these features have endured for billions of years, their shapes hinting at a time when tides or something like them may have shaped the land. The story these shorelines suggest is staggering. Imagine an ocean filling the northern lands, perhaps hundreds of meters deep in some places, connected to rivers and lakes that drained from the southern highlands. Volcanic heat, impacts, and a thicker atmosphere could have kept this water liquid for millions of years. The surface might have been dotted with icebergs in winter, with waves and spray under the pale pink sky. It is a vision both alien and oddly familiar, a reminder that oceans are not unique to Earth, but if such an ocean existed, it is long gone now. To understand why, you have to follow the trail of Mars's atmosphere. In its youth, Mars likely hid a much denser blanket of air, thick enough to trap heat and maintain surface pressure. That pressure is vital. Without it, liquid water evaporates or freezes almost instantly. As Mars cooled and its magnetic field faded, the atmosphere began to escape into space. The solar wind, a constant stream of charged particles from the sun, stripped it away molecule by molecule over hundreds of millions of years. With each lost molecule, the surface conditions became harsher. Temperatures dropped, air pressure fell, and water was pushed toward to fates, freezing solid or disappearing as vapor. An ocean under such conditions would gradually shrink, retreating into isolated lakes and eventually into ice. Some of that ice became locked in the polar caps where it remains today. Some seeped underground, frozen into the soil, and some may have escaped entirely, joining the atmosphere's slow drift into space. NASA's MAVEN spacecraft, which has been orbiting Mars since 2014, has confirmed that atmospheric loss is still happening. Though the rate today is tiny, the accumulated effect over billions of years is enough to explain much of the missing air. Mars's sky, once blue and dense, became thin and dusty with barely enough pressure to whisper against the rocks. Standing under that sky today would be an eerie experience. The light would feel strange, dimmer than on Earth, yet still sharp. The sun would appear about 2/3 the size it does from Earth, its brightness filtered through a haze of reddish dust. The air would not carry the scents we're used to because it is too thin to carry much at all. If you tried to breathe it without a suit, it would not be the cold that killed you first, but the lack of pressure. Your lungs simply could not draw in enough oxygen to survive. The wind, too, would be deceptive. At its strongest, it might reach speeds of 100 kph, but with so little air to push against you, it would feel like a gentle breeze. It is a curious paradox, a planet capable of global dust storms that can shroud its entire surface, yet whose air is so tenuous you can barely feel it on your skin. The thinness of the atmosphere also changes the way the sky looks. By day, the horizon is a muted, rusty tan, blending into the salmon-colored ground. Near the sun, the dust scatters light in such a way that the sky can appear butterscotch or even faintly yellow. At sunset, the effect reverses. The dust scatters red light away and lets blue light pass through, giving Mars the rare trick of having blue sunsets. Of course, here is the next section of your script, rewritten in the same style. The same iron oxide that makes Mars so visually striking could become a stubborn and dangerous nuisance in daily operations. Risks if inhaled, and its electrostatic nature means it could stick to spacesuits and be carried into living quarters. And yet, for all its challenges, the dust is also part of what makes Mars so visually compelling. It smooths sharp edges, softens colors, and creates subtle, shifting patterns across the surface. In some regions, wind-blown dunes ripple like frozen waves, their dark basaltic sand standing in stark contrast to the pale dust that settles between them. In others, dust collects in the sheltered leeward sides of rocks, drawing faint outlines like shadows cast by the wind itself. The dust is also an archive of Mars's history. Trapped within it are tiny fragments of rock from across the planet, mixed and remixed by winds over eons. By studying its composition, scientists can learn about the geology of places far from their landing sites. As though Mars has spent billions of years passing around samples for inspection, it is possible that the dust even holds chemical clues to the planet's past habitability. If microbial life ever existed on Mars, traces of its activity might have been preserved in mineral grains or locked in fine layers of sediment. Though the odds of such a discovery are uncertain, the dust offers a tantalizing target for future analysis, a record of the planet's surface processes and perhaps, just maybe, of its biological history. From the soft haze it creates in the sky to the massive storms that can blanket a world, Martian dust is a constant presence. It is both a storyteller and a troublemaker, preserving the past while complicating the future. Every rover wheel that leaves a track in it, every gust of wind that stirs it into the air, continues a cycle that has been running since the first rocks on Mars began to crumble. And perhaps that is the essence of the dust planet. It is a world where even the smallest particle matters, where the color of the sky and the fate of a mission can hinge on something so fine you could hold millions of grains in the palm of your hand. On Mars, dust is not just part of the landscape. It is the landscape, endlessly shifting and endlessly patient, waiting for the next wind to lift it once more. On Earth, the tallest mountain is Mount Everest, its peak rising just over 8.5 kilometers above sea level. Impressive, certainly, but on Mars, Everest would look almost modest. There, in the Western Hemisphere, towers Olympus Mons, a volcano so large it defies easy comparison. From base to summit, it stands about 22 kilometers high, nearly 3 times the height of Everest. Its base is so wide, it could cover the entire state of Arizona or the country of France. And if you were standing on one side, the curvature of Mars would hide the other. Olympus Mons is what geologists call a shield volcano, built up over millions of years by repeated lava flows that spread outward in gentle slopes rather than steep cliffs. The lava on Mars is relatively fluid, allowing it to travel great distances before cooling and solidifying. With no tectonic plates to shift the crust beneath it, the volcano stayed fixed over its heat source, erupting in the same spot again and again. On Earth, moving plates carry volcanic hotspots along, creating chains of volcanoes like Hawaii. On Mars, the stationary crust allowed Olympus Mons to keep growing taller and wider without interruption, eventually becoming the largest volcano in the solar system. It is not alone in its grandeur. To the east of Olympus, Mons lies the Tharsis region, a vast volcanic plateau dotted with other colossal peaks, Archaea Mons, Pavonis Mons, and Ascraeus Mons. Each of these volcanoes would be a wonder in its own right if they stood on Earth, but here they are almost overshadowed by their gigantic neighbor. Together, they rise from the same uplifted regional bulge in the crust, so massive that it may have influenced the planet's tilt and even contributed to the formation of the enormous canyon system known as Valles Marineris. These volcanoes tell us a great deal about Mars's geological past. Their sheer size and number indicate that the planet was once far more active than it is today. Volcanism requires heat from within, and in Mars's early history, that heat was abundant. Molten rock pushed upward through weak points in the crust, pouring across the surface in flows that could stretch for hundreds of kilometers. Some eruptions may have lasted for weeks or months, releasing vast amounts of gas and ash into the atmosphere. If there was water present on the surface or in the ground, these eruptions could have triggered floods of melted ice, carving channels, and reshaping the landscape in dramatic bursts. But for all their power, the great volcanoes of Mars are now silent. The last known volcanic activity on the planet may have been as recent as a few million years ago, practically yesterday in geological terms. Without tectonic movement and with much of its internal heat dissipated, Mars's mantle has grown still, unable to feed the colossal structures it once built. The stillness is striking. Imagine standing near the base of Olympus Mons, looking up at a slope so gentle that from your vantage point, it might seem more like a hill than a mountain. Yet that slope stretches for hundreds of kilometers before it finally reaches the summit. Climbing it would be a strange experience. The low gravity would help, but the scale would be disorienting. You could walk for days and feel as though you were barely making progress, the horizon forever retreating. The caldera at the summit, the collapsed crater left after eruptions emptied the magma chamber below, is large enough to swallow entire cities. It is ringed by cliffs and fractured by ancient faults, a reminder of the forces that once surged beneath. Now it is silent, dust settling in thin layers over rock that has not felt the heat of magma in ages. If the Grand Canyon on Earth impresses you with its sheer scale, Valles Marineris on Mars would leave you speechless. Stretching for over 4,000 km, it is nearly 10 times longer than the Grand Canyon. In places, it is more than 200 kilometers wide and plunges as deep as 7 kilometers. If it were on Earth, it would run almost the entire width of the United States, from New York to California, swallowing whole mountain ranges along the way. Seen from orbit, it is a scar so vast that it dominates the face of the planet. The name comes from NASA's Mariner 9 spacecraft, which first revealed its staggering size in the early 1970s. Until then, nobody expected such a feature on Mars. The canyon's proportions defy easy comparison, not just because of its length and depth, but because of its complexity. Valles Marineris is not one continuous trench, but a network of interconnected chasms, each with its own cliffs, slopes, landslides, and layered walls. From above, it resembles a series of parallel cracks that have been widened and deepened over unimaginable spans of time. How such a feature formed remains one of the great geological debates in planetary science. On Earth, canyons are typically carved by rivers, glaciers, or a combination of both. But Mars does not seem to have had enough flowing water for long enough to cut something of this scale. Instead, most scientists believe Valles Marineris began as a giant tectonic fracture. In the planet's distant past, the immense volcanic activity of the Tharsis region to the west may have uplifted the crust, stretching it until it cracked. Once those fractures formed, they could have been widened by landslides, the collapse of underground caverns, and even bursts of water or lava that eroded the walls. The canyon's walls are a geological archive, revealing layers upon layers of rock laid down over billions of years. Each stratum tells a story of a different era. Volcanic ash from distant eruptions, sediments from ancient rivers, and deposits shaped by wind over long dry periods. Landslides have exposed these layers in spectacular cross-sections, creating cliffs that could be taller than Mount Everest. From the bottom, the view upward would be dizzying. sheer walls stretching kilometers above, their colors shifting from deep reds to pale yellows in the thin sunlight. The scale of Valles Marineris is difficult to fully appreciate without being there. Imagine drifting along in a spacecraft at low altitude, following the canyon floor for days as its walls rise and fall around you. In some stretches, the canyon widens into vast basins where side canyons branch away like tributaries. In others, it narrows to tight corridors where the walls crowd close, casting long shadows even at midday. In the thin Martian air, light scatters differently, and the shadows would have a softness to them, their edges blurred by the ever-present dust. At the top and bottom of Mars lie two gleaming caps of ice and dust, the planet's frozen crowns. From orbit, they stand out sharply against the rust-red terrain, bright spirals and swirls that look almost delicate, as if they were painted onto the surface with a steady hand. In reality, they are massive deposits of frozen water and carbon dioxide stacked in layers that record the planet's climate over millions of years. The North Polar Cap, known as Planemborium, is the larger of the two. In the height of northern summer, it is made mostly of water ice, its surface etched with graceful, curving troughs carved by winds. The South Polar Cap, Planum Australe, is smaller but thicker, and its base may contain a layer of carbon dioxide ice that has persisted for millennia. Both caps sit atop layered deposits, like the rings of a tree built from alternating seasons of snowfall, frost, and dust. These layers are a kind of natural archive, preserving a record of Mars's shifting tilt and changing climate. Unlike Earth's poles, which are cloaked in thick ice year-round, Mars's poles undergo dramatic seasonal transformations. This is because much of the ice you see in pictures is not water ice at all, but dry ice, frozen carbon dioxide. Each Martian year, as winter grips one pole, temperatures plunge so low that carbon dioxide from the atmosphere freezes directly onto the surface, adding a seasonal layer up to a meter thick. At the same time, the opposite pole is in summer, and its dry ice layer sublimates, turning straight from solid to gas to rejoin the atmosphere. This annual breathing in and out of carbon dioxide is so significant that it changes the pressure of the planet's atmosphere. In winter, when carbon dioxide freezes at one pole, the total atmospheric pressure drops. In summer, as that frozen carbon dioxide returns to the air, the pressure rises again. The poles act like giant valves, cycling a large portion of the atmosphere between solid and gas. This process is most striking to watch during the transition between seasons. As sunlight creeps back across a winter pole, the dry ice begins to sublimate from the bottom, trapping gas beneath the remaining ice. Eventually, the pressure builds enough to crack the surface, releasing sudden jets of gas that carry dust and sand with them. From above, these eruptions leave dark, fan-shaped stains on the ice, marking the direction of the prevailing winds. It is a strange and beautiful phenomenon, unique to a world where the atmosphere itself regularly freezes solid beneath the seasonal layers of dry ice. The permanent water ice of the poles holds an enormous reservoir. If all the water ice from Mars's poles were melted, it could cover the planet in a global ocean over 10 meters deep. This water is a key target for future exploration, not just because of its scientific value, but because it could sustain human missions. Ice could be mined for drinking water, broken down into oxygen for breathing, and used to make rocket fuel. The poles also reveal patterns in Mars's longer-term climate history. The planet's axial tilt, or obliquity, changes dramatically over cycles lasting hundreds of thousands to millions of years. At times, Mars tilts more steeply, causing the poles to receive more sunlight and warm enough to release large amounts of ice into the atmosphere. At other times, the tilt lessens and the poles grow colder, locking more water into their icy layers. The stratified deposits at both poles capture these shifts in fine detail. Each layer a frozen page from Mars's climate record. High above Mars, two small moons circle through the thin, dusty sky, Phobos and Deimos. They are nothing like our own large, bright moon. These companions are irregular, lumpy, and dark, more like misshapen asteroids than miniature planets. In fact, if you were expecting a majestic lunar disk rising over the Martian horizon, you might be surprised to see instead a potato-shaped rock drifting silently overhead. Phobos, the larger of the two, is still quite small by moon standards. It is only about 22 kilometers across at its widest point, a size that would barely register as a dot if placed next to our moon. Deimos is even smaller, roughly 12 kilometers across, and looks more like a giant space boulder than anything else. Their surfaces are pocked with craters, their shapes irregular, and their colors muted to a dull gray-brown. They lack the spherical symmetry of larger worlds, their low gravity unable to pull them into a perfect roundness. Because they are so small, both moons have an uncanny quality when seen from the Martian surface. Deimos, the more distant of the two, rises and sets much like our moon does, though it appears only as a bright, star-like point to the naked eye. Phobos, however, orbits so close to Mars that it races across the sky in just over 7 hours. It rises in the west, sets in the east, and can be seen crossing the heavens several times in a single Martian day. Standing on Mars, you could watch Phobos rise in the late afternoon and then see it set again before midnight. Where these moons came from is still a matter of debate. One theory suggests they are captured asteroids, pulled in from the nearby asteroid belt, or perhaps even from farther out. Their shapes and dark surfaces resemble a class of asteroids called carbonaceous chondrites, which supports this idea. Another theory is that Phobos and Deimos formed much closer to Mars, born from debris left behind after a massive impact. In this scenario, a large asteroid struck Mars billions of years ago, ejecting vast amounts of rock and dust into orbit. Over time, that material clumped together into the two small moons we see today. Whatever their origins, the two moons lead very different orbital lives. Deimos, the smaller and more distant, is slowly drifting away from Mars. In millions of years, it may wander off entirely, slipping into a solar orbit and leaving Mars behind. Phobos, on the other hand, is on a doomed inward spiral. It orbits only about 6,000 kilometers above the Martian surface, so close that it is actually below the planet's synchronous orbit. As a result, Mars's gravity is gradually pulling Phobos closer. Each century, Phobos drops about 2 meters toward the planet. That may not sound like much, but given enough time, the outcome is inevitable. In roughly 30 to 50 million years, Phobos will either crash into Mars or break apart under the stress of tidal forces, forming a temporary ring around the planet. When people imagine Mars, the color that comes to mind first is red deep, rusty, and unmistakable. It is such a defining feature that the planet is known as the Red Planet in almost every language. But that signature color is not the natural hue of every rock and hill. It is the work of a fine, powdery coating that blankets almost the entire planet. Dust rich in iron oxide. The chemistry behind it is simple enough. The rocks of Mars contain iron, just as many rocks on Earth do. Over billions of years, those rocks have been broken down into tiny grains by wind, impacts, and temperature changes. In the presence of trace amounts of oxygen supplied by the thin atmosphere, the iron oxidizes, forming the reddish compounds we call rust. This process has been happening for so long that the surface of Mars is covered in a layer of iron-rich dust just a few microns thick, enough to give the entire planet its burnt orange glow dot from space. The effect is striking. Against the blackness of the cosmos, Mars gleams like a glowing ember. But up close, the colors are far more complex. The rusty tones dominate, but they are not uniform. In some regions, the dust has been swept away by wind, revealing darker volcanic rock beneath. These exposed areas can appear charcoal gray or even black, their basaltic composition absorbing more sunlight. Other places are paler, their dust mixed with lighter minerals that soften the red into peach or tan. Minerals also bring unexpected colors to the Martian palette. Certain salts and clays can appear in shades of greenish gray or bluish tones, especially when viewed under the bright midday sun. Sulfates, which form in the presence of water, can leave behind pale yellow or whitish deposits. In some craters, orbital images have revealed streaks of almost pure white, likely patches of exposed water ice or frost clinging to shaded slopes. Even the polar caps from a distance gleam brilliant white in winter, only to take on subtle pinkish hues as dust settles across them in summer. Mars has always been a world we've known mostly through pictures, silent panoramas of rock and sky. For decades, we could only imagine what it might sound like to stand on its surface. That changed in 2021 when NASA's Perseverance rover began recording with its microphones. For the first time, we could not just see Mars. We could listen to it. The first thing those microphones revealed is something that was already suspected. Mars is incredibly quiet. On Earth, even in the stillest moments, there is background sound, the distant rush of air, the hum of life, the murmur of water, insects, or machines. Mars has none of that. The soundscape is dominated by a deep, almost constant silence. When something does break it, the noise feels sharper, more isolated, as though the whole planet is holding its breath. One of the most striking recordings is of the Martian wind. It is not a roaring gale or a howling storm, but a low, soft hiss, like air moving gently through a narrow space. On some days, gusts sweep over the rover, and you can hear a faint rise and fall in pitch as they pass. These sounds carry a strange intimacy, not the grand, cinematic winds of science fiction, but something far more real, the quiet whisper of an alien atmosphere moving across rock and dust. Occasionally, Perseverance's microphones have picked up the sound of the rover itself, the creak of its wheels turning, the crunch of dust and gravel under its weight, the subtle rattle of its instruments adjusting. On Mars, these mechanical noises are surprisingly subdued. This is because sound travels differently here. The Martian atmosphere is incredibly thin, less than 1% the density of Earth's. It is also made mostly of carbon dioxide rather than nitrogen and oxygen. That combination changes the way sound waves move, making them travel slower and dampening higher-pitched tones. If you were standing next to someone speaking on Mars without a spacesuit, you would hear their voice as softer and lower than on Earth, and it would take slightly longer for the words to reach you. For as long as humans have gazed at Mars, the question has lingered. Is it alive? Not in the way Earth bursts with greenery and creatures, but in the quiet, hidden way that life can sometimes take root in the most unlikely places. For much of history, This question belonged to speculation and imagination. But in the 1970s, it finally stepped into the realm of experiment. In 1976, NASA's Viking 1 and Viking 2 landers touched down on the Martian surface. They were the first successful spacecraft to both land and send back images from the ground. But they carried something more ambitious than cameras. Each Viking lander had a set of biology experiments designed to test for the presence of life. These weren't microscopes searching for tiny Martian worms. Instead, they looked for signs of microbial metabolism, the chemical fingerprints of living processes. The results were confusing. One experiment seemed to give a positive signal, suggesting that something in the soil was breathing, but the others didn't match. The more they studied the data, the more it seemed possible that the reactions were caused not by biology, but by unusual chemistry, driven by Mars's environment. Decades later, the debate still hasn't been fully settled. Some researchers argue that the Viking results were indeed consistent with microbial life, while most remain convinced it was a chemical trick, the soil reacting with nutrients in ways that mimic biology but are purely chemical. In the years since Viking, our approach has become more cautious. Instead of going straight for the "is it alive?" question, missions like the Mars rovers have focused on, was it ever habitable? That means looking for liquid water in the past, organic molecules, and environmental conditions where life could survive. And over time, we found compelling hints. One of the most intriguing modern clues comes from methane. On Earth, methane is often produced by living things, from microbes in the guts of animals to deep-sea bacteria that thrive without sunlight. It can also be produced by geological processes, like the reaction of certain minerals with water. In the thin Martian atmosphere, methane is unstable. Sunlight and chemical reactions break it down in a few hundred years. That means if we detect methane on Mars today, it must be coming from somewhere active, either geological or biological. Long before we had the technology to make it possible, people imagined walking on Mars. Early visions of Martian colonies appeared in science fiction of the 19th and early 20th centuries, when writers painted vivid pictures of domed cities under dusty skies, canals flowing with water, and exotic alien landscapes. In those days, Mars was still a mystery, its surface blurred in telescopes, and its nature open to speculation. The idea of humans living there was as much fantasy as science, but it planted a seed in the human imagination that has never stopped. Growing as our knowledge of the red planet increased, the fantasies began to merge with engineering reality. By the mid-20th century, serious scientists were sketching out plans for crewed missions to Mars. Visionaries like Wernher von Braun proposed enormous spacecraft, carrying teams of astronauts for long stays on the surface, while others imagined fleets of ships ferrying settlers to begin building permanent outposts. In these early concepts, the biggest hurdle was simply getting there. A months-long journey through deep space, relying entirely on life support and careful planning. Today, the dream has evolved into something more tangible. Space agencies and private companies have drawn up detailed mission plans, and rovers have scouted potential landing sites. We know far more about what a human crew would face, and the list of challenges is daunting. One of the most serious threats is radiation. On Earth, our thick atmosphere and strong magnetic field shield us from most of the sun's harmful particles and the cosmic rays streaming in from deep space. Mars, with its thin air and absent magnetic field, offers almost no such protection. Astronauts would be exposed to radiation levels far higher than on the International Space Station. raising risks of cancer and other health issues. Shielding habitats with thick walls, burying them under Martian soil, or building them inside natural caves could help. But all of these solutions require considerable effort and resources. Then there is the dust, fine iron-rich particles that coat the planet's surface. Martian dust is not just a nuisance. It is electrically charged, clingy, and possibly toxic due to compounds called perchlorates. It can clog machinery, scratch spacesuit visors, and irritate lungs if it somehow finds its way inside a habitat. Keeping it out would require careful suit designs, airlock systems, and constant maintenance. Yet, despite these formidable obstacles, the pull of Mars remains strong. Imagining the first human day on the red planet is enough to stir excitement in even the most cautious minds. Picture stepping out of a lander onto dusty soil that has never known a human footprint. The sky overhead is a butterscotch color, the sun smaller and dimmer than you have ever seen. The air is thin and unbreathable, but through your helmet, you feel the stillness a quiet deeper than anything on Earth. Your first steps feel light, almost like slow motion. Each stride sends up a small puff of rust-colored dust that hangs in the weak gravity before settling back down. You might turn in place, taking in the vast emptiness, jagged hills in the distance, a horizon farther away than it seems thanks to the planet's smaller size. The cold is sharp, even through layers of insulation, and you know that survival here will depend entirely on the technology keeping you alive. Inside your habitat, the atmosphere is warm and Earth-like. Outside the thick walls, it is a freezing desert at -60 degrees Celsius on average. Every system, from oxygen recycling to water recovery, has to work flawlessly. You drink coffee made from water, melted from ice mines nearby, or perhaps extracted from the very air. Each sip tastes like history in the making. Work begins quickly. Instruments are set up to measure weather, monitor radiation, and study the soil. Solar panels unfold to catch the weak sunlight, and perhaps a small greenhouse begins sprouting the first Martian-grown plants. You're part of an experiment unlike any other, not just scientific research, but the trial run of a human foothold. On another world, as night falls, the temperature plunges even further, and the stars appear with piercing clarity. Phobos and Deimos, the two tiny moons, drift overhead. You might pause to think about the millions of kilometers between you and Earth, the impossibility of stepping outside without a suit, the delicate bubble of life around you. And yet, in that fragile bubble, there is also the most remarkable fact of all: humanity is here. In that moment, you understand why generations have dreamed of this day. It is not just about exploring another planet. It is about proving that life can take root beyond its birthplace, that our story is not confined to one world. The challenges are immense, the risks real, but the view from that alien soil makes it clear why we will keep trying until it happens. Before human boots ever touch the soil of Mars, our mechanical emissaries have already been there for decades. They have no lungs to breathe its thin air, no eyes to see the butterscotch sky in the way we would. Yet they have been our explorers, our photographers, and our geologists. The story of Mars exploration is one of patient, persistent visits, each mission building on the discoveries of the last until the red planet began to feel less like a distant light in the sky and more like a familiar, if mysterious, neighbor. The earliest visits were brief and cautious. In the 1960s and 70s, spacecraft like Mariner 4, 6, and 7 performed quick flybys, snapping the first close-up images of Mars. What they sent back was startling: a cold, cratered world that looked at first glance much like the moon. It was a sharp contrast to the canals and oases some had still imagined. Mariner 9, arriving in 1971, changed that picture dramatically. It became the first spacecraft to orbit another planet, and as the global dust storm of that year began to settle, it revealed towering volcanoes, vast canyons, and dry river channels. Mars was suddenly a far more interesting place. Then came the first attempts to land. The Viking missions of 1976 were a marvel of engineering. Viking 1 and 2 not only touched down safely, but also carried out experiments to look for signs of life. The results were ambiguous, sparking debates that continue to this day. But the missions proved that a controlled landing and long-term operations on Mars were possible. After a long pause in Mars exploration, the late 1990s marked the start of a new era. This was the age when our explorers began to roll across the Martian surface. The first rover Sojourner arrived in 1997 as part of the Pathfinder mission. Small, slow, and endearingly cautious, it was the robotic equivalent of a toddler taking its first steps, and those steps proved we could navigate the rugged terrain. But it was in 2004 that Mars received two of its most beloved visitors, Spirit and Opportunity. These twin rovers were designed to last 90 days, but they quickly showed they were not bound by such modest expectations. Spirit explored for over 6 years, climbing hills and weathering fierce dust storms before becoming trapped in soft soil. Opportunity, meanwhile, outlived its sibling by a staggering margin, roving tirelessly for nearly 15 years. It traveled more than 45 kilometers, sending back panoramic views, mineral evidence of ancient water, and a steady stream of quiet determination. In 2012, Curiosity arrived, bringing with it a new level of sophistication. This nuclear-powered rover was larger than a small car, bristling with cameras, drills, and laboratories. It was tasked with determining whether Mars had ever been capable of supporting microbial life, and it quickly found evidence in the form of ancient lake beds and clay. Minerals. Curiosity also carried a sense of personality. Its social media updates and images of itself against alien backdrops gave the mission a human-like charm. It remains active to this day, slowly climbing the slopes of Mount Sharp, piecing together the planet's environmental history layer by layer. Then came Perseverance in 2021, the most advanced rover ever sent to another world. Landing in the Jezero crater, an ancient river delta, it was specifically tasked with the search for signs of past life. It drills into rock, caches samples for a future mission to bring back to Earth, and even brought along a small helicopter named Ingenuity. Originally planned to fly only a handful of times, Ingenuity has now completed dozens of flights, becoming the first aircraft to operate on another planet. The red that comes to mind when we think of Mars is not the natural hue of every rock and hill. It is the work of a fine powdery coating that blankets almost the entire planet, dust rich in iron oxide. The chemistry behind it is simple enough. The rocks of Mars contain iron, and over billions of years, those rocks have been broken down into tiny grains. In the presence of trace amounts of oxygen from the thin atmosphere, the iron oxidizes, forming the reddish compounds we call rust. This process has been happening for so long that the surface of Mars is covered in a layer of iron-rich dust, enough to give the entire planet its burnt orange glow. From space, the effect is striking. Against the blackness of the cosmos, Mars gleams like a glowing ember, But up close, the colors are far more complex. The rusty tones dominate, but they are not uniform. In some regions, the dust has been swept away by wind, revealing darker volcanic rock beneath. These exposed areas can appear charcoal gray or even black, their basaltic composition absorbing more sunlight. Other places are paler, their dust mixed with lighter minerals that soften the red into peach or tan. Minerals also bring unexpected colors to the Martian palette. Certain salts and clays can appear in shades of greenish gray or bluish tones, especially when viewed under the bright midday sun. Sulfates, which form in the presence of water, can leave behind pale yellow or whitish deposits. In some craters, orbital images have revealed streaks of almost pure white, likely patches of exposed water ice, or frost clinging to shaded slopes. Even the polar caps from a distance gleam brilliant white in winter, only to take on subtle, pinkish hues as dust settles across them in summer. Seasonal changes also bring shifting shades. During the vast dust storms that can envelop the entire planet, the atmosphere takes on a soft orange glow, muting the shadows and flattening the contrast of the terrain. When the storms subside and the dust settles, the freshly coated landscape can look subtly different, the winds having rearranged the colors in broad sweeping patterns. And then there is the sky. Most of the time, Mars's daylight sky is not blue like Earth's, but a warm butterscotch color. This is because the fine dust suspended in the thin atmosphere scatters sunlight differently than the nitrogen and oxygen-rich air on Earth. The red dust scatters blue light away more efficiently, letting the warmer tones dominate. But at sunset, the effect reverses. The sky near the sun turns a soft blue, while the rest of the horizon glows with deep oranges and reds. It is a gentle, almost pastel blue, lasting only a few minutes before fading into the darkness of space. Imagining Mars under a different sky is an interesting exercise. If the atmosphere were thicker and free of so much dust, scattering would dominate just as it does on Earth, and the daytime sky would likely be blue. The red tones of the ground would stand out more vividly, their contrast sharpened by the cool light above. In such a world, the iconic red might not have been the dominant color at all. Today, though, the planet's colors are shaped by its dryness. The dust does not wash away in rain, nor is it buried under snow for long. Instead, it moves slowly in the wind, settling in thin layers over everything it touches. There is a quiet artistry to it, a planet painted not in bold, fixed colors, but in soft layers that shift over centuries. The reds are the dominant brushstroke, but they are balanced by subtle grays, blacks, yellows, and whites. Each hue has a story, from the chemical transformation of iron to the seasonal dance of frost and dust. If you were to look at Mars and imagine it covered in oceans and forests, you'd be venturing into the realm of one of humanity's most audacious ideas. It's the concept of taking a frozen, airless desert and turning it into something more Earth-like, a place where humans could live without spacesuits, and where plants might take root under a breathable sky. The vision is bold, romantic, and, at least for now, still a long way from reality. The starting point for any plan is Mars's atmosphere, or rather, the lack of it. The air here is thin, about 1% of Earth's sea level pressure, and made mostly of carbon dioxide. To make it habitable, we'd need to thicken that atmosphere considerably. One idea is to release greenhouse gases, trapping heat and raising the temperature until frozen. Carbon dioxide and water ice on the planet's surface and subsurface begin to vaporize. This could, in theory, create a chain reaction where warming releases more gases, further increasing the pressure and temperature. The end goal would be an atmosphere thick enough to support liquid water and comfortable temperatures, at least in comparison to the current -60 degrees Celsius average. Science fiction has long embraced dramatic versions of this process. In stories, giant orbital mirrors focus sunlight onto the poles, melting ice caps and turning them into seas. Massive machines pump gases into the air, and within a few decades, lush valleys appear where there were once barren plains. Reality, however, is far more stubborn. Research suggests that even if we used every scrap of accessible carbon dioxide on Mars, we might still not get enough to create a stable, breathable atmosphere. Without a magnetic field to protect it, any thickened atmosphere would also slowly leak into space under the constant pressure of the solar wind. There are smaller scale approaches that don't try to transform the entire planet, but instead focus on creating pockets of habitability. These could be enormous domes or underground cities where the air is controlled and temperatures are regulated. Such paraterraforming sidesteps some of the enormous challenges of changing the whole planet, though it also lacks the romantic appeal of standing outside under an open Martian sky without a helmet. Beyond the technical hurdles, there's the question of whether we should do it at all. Terraforming would be irreversible. We would be completely changing a world, potentially erasing any subtle evidence of its geological or even biological past. Is it our right to take a planet that has existed in its own unique state for billions of years and make it into a copy of our own? The debate is one of ethics as much as it is of engineering. Some argue that if humanity is to survive in the long term, we cannot be confined to a single world. Mars could be our lifeboat, a second home ready to be shaped for our needs. Others see the planet as a wilderness, a unique natural wonder that should be preserved as it is. It's a debate that may take centuries to resolve, and the answer will likely depend on the discoveries we make in the coming decades. The vision of a future Mars, with lakes in its canyons and cities under a sky thick enough to breathe, is a powerful one. It speaks to our deep-seated desire to explore, to build, and to make a home for ourselves wherever we can. But for now, the reality is a little more humble. It's a world of dry red dust, thin air, and a silence so profound that it seems to stretch back to the beginning of time. The dream is still out there, as bright and distant as a star, but the work of getting there begins on the ground, one small step at a time. The story of Mars is not over. It is still in its earliest chapters, written by the wind, shaped by volcanoes, and explored by machines that have yet to feel the touch of a human hand. If you enjoyed this cosmic journey, be sure to like, share, and subscribe for more. Join us next time on Hypnohelix as we dive into a new world and explore another fascinating story.